Welcome back. In this presentation, I'm just going to do a bunch of examples of taking the antiderivative or the indefinite integral of polynomial expressions, and hopefully I'll show you that it's a pretty straightforward thing to do. So let's get started. Let's see. If I wanted to take the indefinite integral, and you could do a web search for integral, and you'll see this drawn properly. Take the indefinite integral of let me make something a big expression. Let's say I want to take the indefinite integral of 3x to the negative 5 minus 7x to the third plus 3 minus x to the ninth. So you might already be intimidated by what I wrote down. Well, one, if you saw the last presentation, or if you understood the last presentation, you probably realized, well, the indefinite integral, even though it looks like fancy math, isn't that fancy, or at least it isn't that difficult to perform. And all you have to realize now is when we took the derivative, if we took the derivative of a polynomial was just the sum of the derivatives of each of the terms, and that actually it turns out it's the same way the other way around. The antiderivative of this entire expression is just the sum of the antiderivatives of each of the individual terms. So we can just take the antiderivative of each term and we'll get the answer. So what does this equal? Well, in this case, 3x to the minus 5 power. So we take the exponent, we add 1 to the exponent, so now we get x to the negative 4, right? X to the minus 4. And then we multiply the coefficient times 1 over the new exponent. So 1 over the new exponent is minus 1/4, right? So 3 times minus 1/4 is minus 3/4. And let's see, here we have x to the third. So instead of x to the third, let's raise it by one number. So we get x to the fourth. And then we multiply the coefficient. You know, we could either just keep the minus and say the coefficient 7, or we could just say the coefficient is minus 7. We multiply the coefficient times 1 over the new exponent. So the new exponent is 4, so we multiply 1/4 times minus 7. So minus 7 over 4. And now, this is interesting. Well, just 3. Well, how do we apply this? Well, isn't 3 the same thing as 3 times x to the 0, right? Because x to the 0 is just 1. And that's how you should view it, and it shows you that this rule is actually very consistent. So, what's the antiderivative of 3? Well, if we view 3 as 3x to the 0, we raise the exponent by 1, so now we're going to have x to the 1, right? And x to the 1 is just x, so I'm just going to leave it as an x. And we multiply it, the old coefficient, this 3, or the derivative coefficient, we multiply that times 1 over the inverse of this new the new exponent. So the exponent's 1, so the inverse of 1 is 1, so it just stays 3, right? We multiplied 3 times 1 over 1, which is still just 3. And then finally, x to the 9th, I think you're getting the hang of this. We raise the exponent by 1, x to the 10th. And then we multiply the current coefficient. Well, the current coefficient is minus 1, right? We just didn't write the 1 there. We multiply the current coefficient, minus 1, times 1 over the new exponent. So it's minus 1 over 10. There we did it. That wasn't too difficult of taking the antiderivative, or, once again, as I always forget, plus c, right? Because when you take the derivative of any constant, it becomes 0, so it might have disappeared here. So plus c, where this is any constant. This could be a 10, could be a million, could be a minus trillion. It's any constant. And just to really hit the point home, let's take the derivative of this and just make sure we got this expression. And this hopefully is second nature to you by now. And if you ever run out of practice problems in your book because you love doing math so much, just make up problems. That's what I'm doing. All right. I do this even when I'm not recording videos, just for fun. Okay, so let's take the derivative of this. Minus 4 times this coefficient. Minus 4 times minus 3/4 is 3x. Then we subtract 1 from this exponent. Minus 5. And then minus 7 4 times 4 is minus 7 x to the, we take 1 from this exponent, x to the third. And I promise you, I'm not even looking up here. I know you might think, well, Sal, he's just looking up here. But no, I'm actually, in my head at least, working through this. And then plus the derivative of 3x. Well, the derivative of 3x is 3, is almost second nature now, but you can kind of view this as 3x to the 1. And you say 1 times 3 is 3 times x to the 0, right? And then 10 times minus 110, well, that's just minus 1. X to the 1 less than 10, so x to the 9th, plus, what's the derivative of any constant? Right, it's 0. Right? You could almost view this constant as, some number times, x to the 0. And if you took the derivative, well, you multiply the 0 times c, and you get 0. And then, well, you might get minus 1, depending on how you're doing it. But that's actually kind of an interesting question. Okay, I'll stop digressing. We get a 0 here, and if you simplify that, that just equals 3x to the minus 5 minus 7x to the third plus 3 minus x to the 9th. I think we have time for one more problem like this. I think you probably got this. This is probably one of the more straightforward things you'll learn in mathematics. And in future presentations, I'll give you more of an intuition of what you can actually, why the antiderivative is useful, and then, we're learning the indefinite integral, but we could learn to use the definite integral, which we'll learn in a couple of presentations to figure out things like the area under a curve or the volume of a rotational figure. Well, I don't want to confuse you too much. Let's do one more problem. I won't make this one as hairy. So the integral of negative 1/2 x to the minus 3 plus 7 x to the 5th. Well, let's start with this term of the polynomial. We raise the exponent 1, so x to the minus 2 now, right? Because we added 1 to negative 3. And then we multiply 1 over this new exponent times the old coefficient. And actually, I'll write out all the steps. So the old coefficient is minus 1/2, right? The old coefficient is minus 1/2. Let me use some colors. So this is a minus 2. Minus 2. So we multiply it times minus 1/2, right? And then let me switch colors back. Plus, we raise the exponent by 1, x to the 6th, and we multiply the old coefficient times 1 over the new coefficient times 1 over 6. It's multiplication. Let me make this yellow 6. And so what's the answer? Well, what's minus 1/2 times minus 1/2? Well, that's positive 1/4 x to the minus 2. Oh, and of course, plus c. As you can tell, this was my main source of missing points on calculus quizzes. 1/4 x to the minus 2 plus 7/6 x to the 6th plus c. There you go. And if you want to take the derivative, minus 2 times 1/4 is minus 2/4, which is minus 1/2 x to the minus 3. And then 6 times 7/6 is 7x, and then you decrease the exponent by 1, x to the 5th, and then the derivative of a constant is 0. And then we get our original expression. So I think, hopefully at this point, you're pretty comfortable, taking a derivative of a polynomial, and then, given a polynomial, you can actually take the antiderivative, go the other way, and never forget to do your plus c's. And I hope you understand why we have to put that constant there, because when you take an antiderivative, you don't know whether the original thing that you took the derivative of, I guess, had a constant there, because a constant's derivative is 0. Hopefully I confused you with that last statement. I will see you in the next presentation, and I'll show you how to reverse the chain rule. See you soon.